Thanks for the kind introduction, Amar, and for the invitation to come here to the University of Toronto, see some of my friends here and talk to colleagues and so forth. So it's good to be back in person. In my university, this is also our first live colloquium happening today. So I think it's kind of an exciting time for all of us. So Amar was talking about something called spam, and I'm going to tell you what spam is a little bit later, but I was instructed to add some whimsy to the title of my talk. So that's why that is on there. So I promise we're not going to talk about the canned meat, at least not very much, but it's going to be an acronym. You'll see in just a moment. So before I get into that stuff, I want to talk a little bit about kind of the degrees of quantumness that exist out there in things that we call quantum mechanical, because certainly when I was a student, I took my undergraduate quantum mechanics class, just like many of you took at some point or will be taking. And I sort of, since that point, I've learned repeatedly how many of the things that I thought were quantum mechanical are in fact classical physics. You know, I think that the undergraduate quantum curriculum is frequently sort of a math methods class, honestly, and you're doing wave equation, which is a perfectly classical equation. And so I want to kind of separate things. So here's the idea. We have classical physics and we can add quantumness in sort of a fake way to it, okay? So we can take classical physics and say particles are going to behave like waves, all right? It's not that big of a deal. We know how waves work, right? So once you make that jump, once you say particles behave like waves, the math you're doing is just classical math again, right? We can add spin to them. We can add all sorts of stuff. And what we get when we do that is what you could call semi-classical physics, okay? It looks a lot like classical physics, except it's got like, you know, some wiggles up there, but you're effectively just kind of doing the same thing, really, all right? You've taken some results from quantum mechanics, applied them, but you're not interacting with the actual quantumness in the system, I would say, okay? You're kind of taking the results as a given, all right? You can even have things like tunneling and so forth. And that's what I'll call sort of quantum 1.0 technologies. So when people talk about, if you've heard of quantum computing, quantum simulation, or quantum technologies like quantum sensing, some of these fall into this box of quantum 1.0. Some of them are going to be quantum 2.0. In quantum 1.0, the quantum mechanics stays in the box, okay? You aren't really interacting with it anymore. You can calculate some potential energy surface, for instance, for a chemical reaction, and then drop a marble on the surface and watch where the marble goes, all right? This is what a lot of sort of, you know, quantum chemistry ends up doing, okay? So it's pretty classical at the end of the day. However, if you have a system that exhibits something called entanglement, if you have a state that looks a little bit something like what I've written here, which all I'm trying to write here is a description of a system of two spins, okay? And these spins I'm going to represent as either being up arrow or down arrow. And if I have the first one, the first arrow represents the first spin, the second one represents the second one, this entangled state tells us that we have kind of spin up, plus spin down, spin down. And once we have a state like that, a so-called entangled state, we're no longer in this semi-classical physics regime. This is a situation where we have to use quantum mechanics and all the weirdest things about it. We get straight to like kind of like the heart of the matter. You can't come up with a classical system like Maxwell's equations that you can use to reproduce the same results. It simply won't happen, okay? You absolutely have to use quantum mechanics in this sense. So you're opening the box. This is what I call quantum 2.0. So in quantum 2.0 technologies, you're actually interacting with the quantum part that lived inside the box. You get to tinker with it. You get to make measurements and poke around in there and do coherent operations and so forth in a way that produces results that you cannot reproduce without quantum mechanics. Okay, Maxwell's equations won't do it anymore. Newton's laws won't do it anymore, okay? So what is that useful for? Well, the first non-trivial example I can give you with two spins is a 3-spin state, okay? So now I'm already adding to the number of spins. Now we're gonna have 3 spins, okay? And I can make what I'll call a classical state. It's something called a product state. And I can build it up as follows. I can take the first spin and I can put it into a superposition state, okay? It's got part of it is sort of looks like it's spin up and part of it looks like it's spin down. That's what the A and B mean, all right? These are like coefficients on a vector, right? They are coefficients on a vector, it turns out. And I multiply that by the state of the second spin, and I multiply that by the state of the third spin. And we know how to multiply. These fancy time symbols just mean keep track of labels. That's all that means, all right? And my labels, you know, in the lower lines here are just which position the arrow is in, okay? And when I do that, I can ask how much information is required to describe the state of the system. And we can count up the coefficients here. And even though there are 8 basis states down here, all the way from down, down, down to up, 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 there are actually only 6 coefficients I need to describe this system, okay? And if you imagine, okay, maybe I had 4 spins, 5 spins. What if I had n spins? You can convince yourself that the number of coefficients is basically something like linear in n, okay? Like 2 times n, all right? We can nitpick about exactly what I mean by coefficient and, you know, normalization and stuff like that, but this is the basic idea. So something like 6 coefficients for this state. If, however, I write down the most general state allowed by quantum mechanics, it actually has 8 coefficients that I need to be able to write down the state of the system. So if I have a quantum system and I just want to simulate it on a classical computer, I have to write down that much information. And this is in the exponent, 2 to the n now, where n is 3 in our example here. I have to write down 8 coefficients. Now this is not a big deal. 6 versus 8 is not a big deal, okay? However, the scaling is what matters. So physicists, we're always talking about scaling, and you can roll your eyes about scaling, but this exponential scaling is pretty insane compared to this linear one. So to give you an example, to get intuitive feel for that, if n is 200 and I have a product state, I have 2 times 200 coefficients. I need to store 400 coefficients in my laptop computer in order to simulate and just keep track of the state of the system. If I have, however, a quantum state of the system, then in general, I need some umpty gajillion, jillion, jillion, okay? Like this number even keeps going after that, okay? It's completely out of control with just 200 spins. And if you think about how many spins there are, you know, in this piece of chalk, you know, Avogadro's number of spins or something like that, it is fairly clear where all this is going to break down, okay? This quantum mechanical system can explore somehow a state space that is absurdly large for even a very modest sized system. And so that's going to make certainly simulating it on a classical computer difficult, but it might make using quantum states for something computational kind of an attractive thing. So what do I mean by that? Well, now we're using our quantum 2.0 idea here, and we're going to look inside the box. And this is my version of what a quantum computer or a quantum simulator is going to do, okay? It's some device here, and we have some inputs here that are what I call a quantum channel. These are going to transport a quantum state of some physical system, sort of, it'll load it into the system, it'll load it into the computer so the computer can run its program. And to initialize that, I can do it qubit by qubit, all right? I can start it off in a classical state. So this is one way to do things. You just make a big product state of the n different qubits on the input here. And the number, the resource cost of doing that scales, basically linear with the number of qubits, all right? That's crucial because if this n is in the exponent, then obviously I'm not even going to be able to run the device anymore when there are 200 of them or even 50 of them, right? You just forget about it. So we need this scaling to be sub-exponential for a device to be useful. The same thing applies to the output. I want to know what the result of the simulation or the computation was, and I perform a series of measurements out here at the other end of this other quantum channel, turns it into classical information. I can read that out. And since I'm measuring each qubit one by one, in fact, I'm measuring some subset of them. Typically, it's even better than that. That also scales something like n. So things are going okay, but what's inside the box can't require an exponential number of classical resources either, right? So this little piece of bacon down here is supposed to represent some kind of a ribbon cable or something, all right? That's a thing that used to exist way back in the day called a ribbon cable. You can look it up online, okay? And it's some classical controls that I need to run this algorithm. And that also is going to scale linearly or sub-exponentially, okay? Basically, we don't want it to blow up with n as quickly. And the magic of a quantum 2.0 device, the magic of this is that on the inside, it does explore that giant Hilbert space. Okay, it's called Hilbert space. It does explore, writing down the state of the system and storing it on, the world's biggest supercomputer is just simply not even possible for a fairly modest sized system. Okay, so this is the point here. Okay, now the way we build these things, I've been using the word qubit. What I mean by qubit is basically a well-controlled two-level system. All right. And there are various platforms out there that exist for building this, okay? One is to use trapped atoms, one can use superconductors, quantum dots. These are kind of just three of the sort of more popular choices that exist out there. But one of the things they all have in common is that they all have some kind of a two-level system in them. And we label those. I like to use up and down arrows to label mine because I'm a physicist, but a computer scientist would call this 0 and 1. Okay, it's all the same, they're just labels. It doesn't matter whether this is literally a spin pointing in a certain direction in space. That's not important for this. This could be two levels of any type, essentially. Now, the reason that these systems kind of are popular has something to do with the fact that people have worked very hard to choose them and engineer them in such a way that they really do boil it down to just two levels. Okay, that's very important because you don't want your quantum information stored in the state of this system to start walking off into the other states of your qubit, because then they're lost from the subset of states that you're actually using in the computation. That's called a leakage error, okay? However, there are uses for having other states. And in fact, you can have systems that have other states with very nice properties. They can be long-lived. The energy splittings can be very stable and robust against fluctuations, things of that nature. So we can think about building, now that we've learned a lot about how to work with qubits, we can think about how can we utilize the kind of internal state space of these devices more efficiently. Because right now we're just using two levels and we're trying very, very hard to ignore all the rest. But I think that one of the things I've learned over the past maybe 5 or 6 years in my own research is how useful those other states are. We call them metastable sometimes, but having other states there so that you can hide information, you can hide the entire qubit from some perturbation that's happening. You can change the character of it from a storage qubit to something that you can actually perform gates on, things like that. And that's really useful. So we can think about making more complicated qubits. And the tool that seems to be the most kind of attractive in the long term for making these things is basically chemical self-assembly or chemical assembly, okay? Can you have something that builds qubits out of essentially chemistry tools? Now all of a sudden you can think about an Avogadro's number of these things. Now, of course, controlling it, reading it out, preparing the states, this is all like very difficult. So probably not Avogadro's number, but if you really want to get to, billions of these things, I think it's attractive to think, well, we'll take some object that's already quantum mechanical. It's got the quantum mechanics already working inside it. It's baked inside the thing. And we are just going to learn how to use these better. So this is a species I'm going to talk about a little bit later. This is another one that we work with. Like, we can think about using really big molecules for this. They'll have a whole bunch of levels inside here. But we can tune them. We can tune their properties because we can use chemistry to do so. And that's something that you just can't do quite as easily with these other platforms here, okay? So we'll try to leverage the tools of chemistry. Now, the first headache we run into in thinking about this seriously is state preparation and measurement. So that's what SPAM is, okay? The and gets an A because people think it's funny to say SPAM, basically, I think. But this is cooling. So in the Physics 198 class, today, Amar, talked a lot about cooling. In state preparation of a multi-level system into a smaller subset of those levels is basically cooling, right? You can start off with something that has a lot of entropy in it, and your goal is to distill it down to something where you really know the state of the system in the most complete way known, kind of allowed by quantum mechanics. So we're talking about entropy flow. We have a system that we would assign some entropy to because we have classical ignorance about which state it's in. And what we want to do is pull that entropy out of there. We want to learn the information, okay? Entropy and information are the same thing, all right? So we have classical ignorance about the state of our molecule because it's got a jillion levels because it's a molecule. And we have to figure out a way to deal with that. That's the price we pay. If we can pay that price, the thing we win is that we know, if you know how to make one molecule, you know how to make Avogadro's number of molecules, okay? So you can scale it up. The hard part is going to be sort of getting past this first hurdle. You can do this by cooling below the energy scale, if that's possible. That's something that is certainly attractive. But you have to be able to do it at the single particle level. So I'm not going to allow just throwing away molecules that don't do what you want, okay? We have to be deterministic about this and non-destructive in these measurement processes, okay? So an example of where this might come in is a sort of quantum 1.0 type application. This was an experiment that really was kind of Amar's idea when he was a graduate student. This was his thesis project right here. It's a beautiful experiment. And this experiment has put the best limit on the electric dipole moment of the electron. And the way they did it was by using molecules. So Amar worked with his advisor and they chose a molecule, it's thorium oxide. And we made this beam of thorium oxide. And it has a lot of the features that I'm talking about here, which is to say there's a part in the middle, which is the quantum gates in some sense, okay? There's a part where we're doing things that are reversible, and there's some unknown signal that can creep in there, okay? Which you could think of as entropy if you want to think about it that way, all right? But the point is that, there's something happening inside there that we have to not disturb because we're using that as a sensor. And then we have our state preparation and readout in this thing. And so those are the kind of spam operations there, the entropic operations, things where there's some transfer of entropy between kind of the environment and the system that we're interested in. So this goes not just for quantum computing, but this is a precision measurement kind of fundamental physics application of some of these ideas. If we got really, really good at doing all this with really big molecules, we would be able to do wonderful things, okay? This is like a tiny molecule, thorium oxide. It's barely a molecule. It's diatomic. It's one atom away from being just an atom, right? Okay, this is not a very complicated thing. If we can start to actually do variations on that theme, it should really open up the space of possibilities. And the way that we do this with atoms is to do something called optical pumping. So if we have some levels down here and we don't know which state the system is in, we want to get rid of that entropy. One of the things that we can do is couple to an excited state that can spontaneously emit photons and go back to these levels. And if you do that in just the right way, you can say, put on a laser that couples you from one particular level up to that excited state, and it will remove population from that level. The population will pop up in the other four states. Okay, now the other four states have a little bit more. So what you do is you do that for all the states you don't want. You pump the population out of those, and when you're left, there was only one state that you didn't touch, right? All the population has to be there. So the entropy was carried away by the photons that were spontaneously emitted here. We don't usually talk about it as cooling, but this is legit cooling, okay? It's a little hard to assign, temperatures in the kind of classic way to these things, but this would be a 0 Kelvin, absolute zero state here if it really was as depicted. Now, for quantum information processing, one of the things I do in my group is I do work with atoms because again, we know how they work, we're actually get really good at those already, okay? So I'm gonna talk mostly about molecules, but if we focus on atoms for a second, I'll give you an idea of how this works. We start off in a kind of unknown state of the ground state of, this looks like hydrogen. This is barium-133, but this looks a lot like the hydrogen atom. What we do is we couple to the excited doublet P1/2 state. We put a laser on that has all three polarizations from this F=1 to the F=1 transition. And if you look at the blue wiggly arrows, that's the spontaneous emission process that is not going to be rescued by this laser. This laser from F=1 to F=1 will be off resonant for rescuing any population in spin up. So you end up with all the population in spin up. And when we go through the error budget of this, we find that our ability to initialize that state is something like a part in 10 to the 5, okay? So that's a very pure quantum state, all right? And we could also do readout and so forth. And in using these techniques, we were able to show that you can get a state preparation and measurement error of less than sort of 3 × 10⁻⁴, which was a record for any type of qubit. So these spontaneously emitted photons are doing the work for you, and they're very, very useful. But when you try this with a molecule, it gets tough. And one of the ways it gets tough is vibration. In fact, this is arguably the hardest one. Molecular vibration doesn't have rigid selection rules, okay? There are selection rules for angular momentum, for something like molecular rotation. But there are not selection rules for vibration that are very rigid. So what we do is we have to choose a molecule that has very diagonal Frank-Condon factors. Diagonal Frank-Condon factors means that the overlap integral between the vibrational wave function in the excited state and the vibrational wave function in the ground state for the decay that we want is nearly 1. Okay, so this is just an overlap between 2 wave functions right here. All right, so those properties are kind of rare, but you can find some molecules that have this property, and that gives you some kind of control over this. Okay, you can sort of plug this leak to some degree doing that. The next headache is rotation. For rotation, we have angular momentum selection rules though, right? So it's actually not that bad. In fact, what you can do is you simply drive transitions from the first excited state in rotation up to the ground state in the electronically excited state. The reason that doesn't cause problems on spontaneous emission is because J prime equals 0 can only go one place. If delta J has to be 1, because the photon carried away h bar worth of momentum, then delta J can only put you in the J equals 1 ground state here. So that one we can plug. And that's called, by the way, that's called a P branch transition, okay? So there are names for these things, but when you drive from a J to J minus 1, that's called a P branch transition in molecular spectroscopy. All right, past that, there's all kinds of more. I mean, there's other, this is not an exhaustive list. Hyperfine structure, we have Zeeman sublevels, all sorts of stuff. However, for most of those, it's actually not that hard to plug those holes with light. We can modulate our lasers to take care of a lot of those things. So really the hard part is vibration. Rotation we know how to deal with. So we're starting to develop our toolbox here. The next thing that we need is a closed optical cycle, which is related to this idea of a diagonal Frank-Condon factor. So an optical cycling transition is a transition between a ground state and excited state where the excited state can only decay back to the exact same ground state, okay? So if the Einstein A coefficient of this state here coupled to the down state is exactly 1 of the lifetime, we have a cycling transition. And one of the things we can do with that is we can illuminate it with a laser and we just watch photons come up. And our detector goes click, 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 okay? Now that requires really diagonal Frank-Condon factors so that this thing doesn't branch off to these other states as we were talking about earlier, right? But if we can do this, we can do our state preparation, we can do our state detection because getting those clicks on our detector gives us the information about what the system is doing, right? And an example of this is to take an atomic ion. Here's a picture of an atomic ion from my group where when we put it in 1 qubit state and then we try to make it fluoresce on the cycling transition, we see it, okay? It's a single atom. And when it's in the other state, it's just completely dark, okay? It's as if it has disappeared. It's completely invisible, all right? And, by looking at how those kind of detected photon clicks are distributed here, we are able to, this is in ytterbium now, we're able to get state preparation measurement and fidelity that is even better than the barium example I showed you earlier. So these histograms, kind of the blue histogram is really well separated from the yellow histogram is the point here. And it's all because of this optical cycling transition. It makes things really, really easy for us. Now, a related thing to all of this is the state preparation of the motional state of, say, an atom or a molecule or something like that in quantum computer. We generally need them to be very, very cold in terms of their center of mass motion. And one of the ways that we do that is using something called Doppler cooling or optical molasses. And for those of you who are in Physics 198, you just talked all about that with us. But the idea here is that we have an atom and we illuminate it from both directions with laser light that is a little bit too red. Okay, this line here is supposed to, the sharp line on the plot represents the laser frequency, and the Lorentzian on the plot represents the atom's rest frame resonance spectrum. So if the atom is not moving, it's not going to scatter very many photons. However, if the atom starts moving in the horizontal direction on the screen, it will Doppler shift one of those beams into resonance with its atomic transition. And it will do so for the beam that is counterpropagating with respect to the atom's motion. It will absorb a photon, which means it gets a momentum kick, and then it emits it in a random direction. And so no matter which direction this atom goes, it gets a kick that is opposed to the direction that it's moving. And those spontaneously emitted photons that go off in random directions carry away the entropy. This is called optical molasses. And there's a classic paper on this that kind of goes through the math on this. And at the end of the day, what you get is a temperature that is given by the line width of the transition. So gamma is the width of this thing times h bar. And it turns out that the scale for this is about 500 microkelvin. So less than 1,000th degree above absolute zero. So we can take a room temperature vacuum chamber, we fill it with room temperature atoms, and we use lasers, and we can produce those things a tiny fraction of a degree above absolute zero. And this is kind of, 1980s technology. Okay, this is actually old news, although it's pretty amazing, I think. Okay. So that is a useful thing for optical cycling. The two things about optical cycling, one of them was state detection, the other one was laser cooling. Now, if we want to do this with molecules, I talked about some of the issues that we run into, the desirable properties, and most molecules don't have those properties, okay? So the list of molecules that have been optically cycled, at least for Doppler cooling, is actually a pretty short list. In fact, this one here that is the biggest one that's ever been done, and it's got what, 5 atoms? 6 atoms, okay? So it's actually pretty modest stuff that we're talking about. So we're not introducing quite as many levels as I think, the world of chemistry can give us. In fact, if you start talking to chemists about most of these molecules, they get very suspicious of them because they don't look like the molecules that they're used to. All of them are radicals, if you know what a radical is. So, we're not quite at the point where we're making qubits out of things that, people know a lot about synthesis and how to make a beaker full of these things. One thing they have in common, though, is they all work on the same motif, which is that you have an alkaline earth metal atom. So that's the second column of the periodic table. So the leftmost column is the alkali atoms. Right next to it is the alkaline earth atoms. And it's bonded to a halogen. So halogens are fluorine, what else? What? Fluorine, yeah, fluorine, chlorine. Okay, exactly. All right, thank you. All right, that column, right? I'm thinking iodine in my head for some reason. Okay, so the halogens actually do something for you that I'll describe in a moment, but they create an optical cycling center on here, and you can replace the halogen with something that isn't quite a halogen, like say oxygen bonded to hydrogen, which when you kind of add it all up in terms of the valence, looks like a halogen, sort of a pseudo halogen, if you will. And in fact, that's sort of how this works. So fundamentally, what's going on here is that you have a part of this molecule that looks like it is missing an electron because the rest of this thing is pulling electrons from it, okay? It's what we call, it has, electron withdrawing properties. The electron from the alkaline earth metal atom would rather live on here, and it leaves all the rest one up there. So you end up with essentially something that ideally looks like a gas phase alkaline earth ion. And I showed you some results from barium ions and terbium ions earlier. Okay, we know how to optically cycle those things. And this electron withdrawing thing is called the ligand, all right? And this ligand can be, the hope here is that we can start to build the technology to put whatever we want on there, okay? I want to make it big enough that I can put anything on there and be able to optically cycle this thing. So I can do state prep and measurement and quantum computing and all this wonderful stuff. that I can get with optical cycling. And the key here is that we've made an ionic bond. We have electron withdrawing down here and electron donating up there. So we've got state preparation and measurement at the top, and at the bottom, who knows what, okay? So I've talked about that example of the thorium oxide experiment that Amar did for his thesis project, where you have some really heavy atom like thorium that's a relativistic atom and therefore is sensitive to like physics beyond the standard model. Here you want to endow it with the ability to actually get single molecule detection working, which is not working currently in that experiment for exactly those Frank Condon factor reasons I talked about earlier. Or maybe this is something interesting chemically and you're going to let it chemically react with stuff. Or maybe it's a sensor for something, who knows, okay? But we want to get to the point where we can do this with a general species. And one of the first investigations we did was my colleague at UCLA in the chemistry department, Anastasia Alexandrova, and her students first kind of came up with the idea that having a benzene ring bonded to oxygen in the alkaline earth atom is actually a reasonable optically cycling molecule. And the reason is that for exactly what I said before, this whole thing down here from the oxygen downward kind of looks like a halogen in some sense chemically. It's going to pull electrons off the top. And if you look at the wave functions of the electrons up there, or the electron density, I should say, it looks a lot like an atomic S and P orbitals, right? I mean, this is kind of spherical, and this thing has like 2 lobes, basically. So we're trying to get a gas phase atomic ion up there. Going through these numbers, they predicted that the branching ratios should be pretty good. So these are sort of the Frank Condon factors that I was mentioning earlier. There was also work by another one of our collaborators, Anna Krylov's group at USC, that suggested the Frank Condon factors were actually not very good. And so we decided to go ahead and do the experiment and find out what was right. Okay. So the spectroscopy experiment was done in collaboration with John Doyle's group at Harvard and my colleagues Eric Hudson and Justin Karam at UCLA. And we created this stuff in a cold cell. We made these molecules in gas phase, and then we're going to shine laser light on them. And we're going to look for those decays. And every different color decay means it's gone someplace else, right? We can track where the thing goes. And our hope is that we get just one line. That's what we want, okay? First, we have to find the excitation wavelength of these species. Nobody has made these species before, so it's actually a little bit tricky, but it was pretty reasonable to do in the end of the day. And then these are kind of the tallies of all the different types of decays. So down here is sort of the actual optical frequency difference between the decay and the transition we want to drive. And the higher these peaks are compared to the rest, the better. We can identify all those different decay modes, and it turns out that these are fairly well closed. So the vibrational branching ratios in these species are kind of, I don't know, 90, north of 90%. Okay, we have 93 and 94 for those two. But I tried to sell you on the idea that we can use chemistry to improve our lives. And make no mistake, I am a physicist, okay? I consider chemists to be borderline sorcerers, okay? So I don't really know what's going on there, but I know that they can do wonderful things. And I want to have access to it. So one of the tricks that we can do now that we have a molecule that's fairly big and complicated, is we can start to tap into organic chemistry, right? We have a benzene ring. This is like the fundamental building block of organic chemistry. And one of the suggestions that Anastasia's group had was we could substitute the hydrogens on the bottom with things that withdraw electrons. So the idea here is that there are secretly hydrogens living on this thing that no respectable chemist ever draws, but that's why I didn't draw it, but secretly they're there, okay? Chemists all know that that stuff is there. And we can put stuff on the bottom. Like for instance, fluorine, right? I already told you that the halogens were electron withdrawing, right? So I can put an electron withdrawing thing on the far side there. And the hope is that it's far enough away from the alkaline earth atom that it can withdraw electrons from it without interfering with the actual orbitals, okay? We don't want it to tug on this thing and have it bend over, right? It's got to be kind of far away. But there are effects in these rings, these carbon rings called resonance and induction, that kind of allow it to communicate in some sense. It's like a data bus, allow it to communicate with the stuff on the other side. And so we came up with a series of different ideas here, ranging from kind of one fluorine, all the way up to this kind of trifluoromethyl substitution here. And they did the calculations of what they thought the Frank-Condon factors were going to be in this case. And we can plot these as a function of, there's a kind of chemistry term called a Hammett parameter that characterizes how electron withdrawing a particular substituent is at a particular site in a phenyl ring. And it looks like as we make it more and more electron withdrawing, which is going from low Hammett total to high Hammett total, the Frank-Condon factors improve. That's the theoretical prediction here. And the kind of winner here is this trifluoromethyl 3 substituted one. So in the lab, we decided to go ahead and look for these things since we were doing the calcium phenoxide. That's the name of this guy here that I already showed you. So we can go all the way from something that actually hates electrons to something that is really withdrawing them because it loves electrons. And the species that we were able to access were to some degree dictated by which kind of reagents we could work with, okay? So these are the things where the precursor chemicals were reasonable for us to work with. So plotting the excitation energies, it turns out that these are actually very easy to predict once you figure out the story here. So instead of having to do completely blind spectroscopy on some species that no one's ever seen before, it turns out this scales with that, essentially that Hammett parameter thing. This is a related concept called the pKa of the ligand. But you basically can predict where the transition energy is going to be with high certainty. And that's kind of mind-blowing to me, because in the world of really small molecules like diatomic molecules, it's like anything goes. I mean, you've got no idea. But here, it's kind of small perturbations we're doing. We're far enough away from the thing that we can tune it. The vibrational branching here, it turns out, is very good, especially for this, this tri-substituted fluorine version of this thing. So that's a fairly electron withdrawing substituent there. And the B to X transition in particular was indistinguishable from 99% vibrational branching ratio for us in this case. We have a fairly big systematic error bar on there, but that is big enough that you can laser cool this. If it really is 0.99 laser cooling, doing a state readout at the single molecule level, this is all going to be possible at that stage. And it's not even a very big molecule yet. So we're just kind of tip of the iceberg here. So getting bigger, we can go to things that have 2 rings on them. These are called naphthoxides. So calcium and strontium naphthoxides, also fairly diagonal, not as heroic as the calcium phenoxide with 3 fluorines on it, but still pretty good. We also looked at some substitutions on there, which didn't seem to make that big of a difference compared to the variations caused by other effects. And in my group back at Harvard, or I'm sorry, back at UCLA with my colleague Eric Hudson, we've been working with the strontium variants of this, and as opposed to calcium, so we're just changing which alkaline earth atom we're doing. The nicer thing about the strontium variants is the wavelengths are technologically easier to hit with lasers. And one of the advantages of that is we can switch to a type of laser that's a lot like this laser pointer probably. And we can do kind of narrow line width scans of that thing. And what we're seeing now is actually individual rotational transitions. So each of those peaks there is a transition on the electronic transition, but it is now resolved at the level of individual rotational lines. So we're zooming way, way in on the horizontal scale here. And we're not nearly at the point where we're seeing, you know, as much detail as is possible, but we're trying to get the spectroscopy done, you know, just learn the very basics about these molecules. Getting even bigger, you can continue this theme and start to grow things maybe to the point where you can really imagine doing funny things, you know, putting relativistic atoms on the far side as sensors and things like that. It looks like this this one here with 1, 2, 3, 4, 5, 6, 7 rings. Okay, I always forget what these are called. I think that might be Ovaline, although I never really remember. It looks like it retains reasonable branching ratio according to those calculations. The experiments on that have not been done yet. But once you get bigger than that, it all kind of breaks down actually. So we're thinking that maybe we would start with something like this, and then we need a different motif. We need some way to make an insulator and then bond it onto something bigger. Okay, so that's kind of our first sort of thing that we learned about how to scale these up and where that breaks down. If we can do this, then we can think even crazier, right? If I can make an insulating break and bond it to stuff and get the system to the point where it no longer cares what it's bound to, I can bond it to the Earth, right? You're going to put it on a substrate, and the substrate is, sitting on a surface in the lab. And if we can do that, then we can do these kind of little quantum sensors, right? You can put it on the tip of an atomic force microscope or something like that. We could couple these to photonic waveguides and things like that if you have ever heard of such devices. But the point is that you might be able to lithographically pattern these. You might be able to use chemical assembly to do these and build yourself a quantum 2.0 type device in a way that might actually scale really easily using the magic of chemistry, and you can tune the properties of these around so that you can get what you want out of them. That's sort of like the dream here. So it's looking reasonable. We hit our first kind of barrier here with the size of these arenes, but there's no reason to believe that we can't actually continue variations on that and find ways to make these even bigger. So next we can ask, well, what would happen if we really had all the Frank quantum vectors that we wanted? What if we got to forget about vibrational branching because we got really good at this? We could tune these with chemical substitution. Well, could we do things like this? I don't even know what this is, okay? All right, it looks, but is there any reason to think that we can't do things like that? All right, I think you'd all like to trap and do horrible things to that thing, right? Okay. Well, I think that there's some possibility that we can do something, and we can start to make these bigger. And at some point, we may have, multiple optical cycling centers on things that are that big, and maybe we can use that as tracers chemically. You can look at quantum effects or sense magnetic fields on a tiny molecular level, whatever it is, right? So one of the things that you run into is the rotational splitting. So I showed you that spectrum a few slides ago where we were rotationally resolved spectrum here. Now the splitting between these is about 1 gigahertz, okay? So that's just like the units that we use. And the actual rotational constants here are kind of about that scale, right? And if we make this thing a lot bigger, the moment of inertia for rotation of this molecule gets so big that those splittings merge together, okay? At some point, they're going to be so narrow, or I'm sorry, they're going to be so close together that the excited state lifetime, just from the delta E, delta T uncertainty principle, is going to make it so we can't resolve those. And if we can't resolve the delta J equals +1 transition from the delta J equals -1 transition, we're going to get rotational branching again. So this was a problem that I claimed was solved earlier in the talk, but if we look ahead, it's going to get unsolved, okay, as we make these things bigger. So that's going to be problematic. So what are we going to do here? Well, if we think about a molecular spectrum here, this is the P transitions. This is what we call the P branch. This Q1 is kind of delta J equals 0, and this R1 is delta J equals +1. Well, the lifetime of the excited state might be so big that we don't see any of those anymore. We can't resolve the P branch. So the statement of that quantitatively is basically that 4 pi times the rotational constant is now sort of comparable to or smaller than gamma. Now, thinking back to Doppler cooling was a little bit in this regime, all right? Not for rotation, but for translation, which is to say that we were actually not resolving the motion of the atom at a level that was particularly heroic, but we were still able to achieve 500 microkelvin in temperature despite that. And so if we think about rotation and we want to cool rotation of something like that, we can think, instead of thinking of this linear momentum transfer of photons, kind of the K vector of the photon, we can think of the angular momentum transfer of the photons. Photons, we like to say they have spin, okay? Photon spin is this kind of spooky thing, but you basically have h bar of angular momentum in the kind of propagation direction or counter-propagating to it, okay? It's kind of only allowed to have those two values. And if we can do the same thing that we did for rotation that we did for translation, then we don't need to resolve those transitions anymore, just like we weren't resolving them for translation. So the way this works is essentially just by doing a big ol' analogy, okay? So we can identify in both cases for translation and rotation, a momentum, an inertia, velocity, so on and so on and so forth. And it turns out the situation is analogous to this, okay? We can actually put this thing through our theoretical framework and we derive all the same equations that we would have done for translation. We can it is now a damping torque instead of a damping force on these things. We have a diffusion constant, we have a Doppler limit, and the Doppler limit, it turns out, is given by the exact same formula, okay? So the minimum temperature we achieve in rotation as a result of this thing I'm calling photon spin molasses is precisely the same level that we achieved for translation of atoms. And that means that we're talking about 500 microkelvin. So instead of having samples of molecules with rotation on the order of Kelvin, we might be able to actually significantly cool these things down, which is really important for removing that entropy. Because as those levels get really close together, for finite temperature, you end up in a huge state space there. Right? So we simulated, along with Ben Elgenbren at Harvard, we simulated how this thing might work. And in about 10 milliseconds of kind of illuminating some big molecule with this, we see that we're piling up population down in the low rotational states here. And the simulated results for the limiting temperature follow exactly with those analytic curves there. So it does look like kind of a one-to-one analogy. And we do this for real molecules that have like kind of non-ideal structural aspects. They have different excited state rotational constants than ground state, and we have all sorts of other stuff that I don't even need to mention. What we find is that the blue kind of initial distribution does get narrowed when we do this. It doesn't necessarily get narrowed around 0. Sometimes it gets narrowed around finite angular momentum, but that's still cooling, okay? What you care about for cooling is the width of the distribution, not the location of the distribution. So you're removing entropy in those cases as well. And we can do this, even with something that has what we call parity doubling as well, and we get some kind of fun effects here. So it looks like this thing, we don't have to worry too much, at least at this stage, about getting rid of our P branch selection rule. It's not going to be a problem for us. And it tells us something about the fact that we have something that will work for big molecules now that wouldn't have worked for smaller molecules. And that's this photon spin molasses. So some things might get easier as we get to bigger and bigger molecules. One of the things that gets easier is we can tune it with chemistry. Another thing that gets easier is we can assemble it with chemistry. And another thing that gets easier is we can start to actually apply some of what we know from regular laser cooling to these other degrees of freedom. But it's all kind of in the very beginning now. So we have a lot of exploratory work to do. A lot of what I showed you here is just kind of calculations and theoretical predictions. We have to actually find these things. We have to try them out. We have to see how well they work. So the folks who worked on the experiments, whose data that I showed you are shown here. In particular, I want to highlight our postdoc Guoju Zhu, as well as Claire and Han, who did the theory work in Anastasia's group. And then Ben and Debayan were big parts of, along with Guoju, of the spectroscopy of those phenoxides and naphthoxides. So with that, I'm happy to take questions. I appreciate your attention.